Welcome to a new episode of this series hosted by CID, Centro Italiano per l'Intelligent Design, aimed at discussing intelligent design directly with some of its major and worldwide famous proponents and on a strictly scientific level. We have the privilege and pleasure today of talking with Professor Michael Behe. Mr. Behe received his PhD in biochemistry from the University of Pennsylvania in 1978. Today, he is professor of biological sciences at Lehigh University in Pennsylvania and a senior fellow at Discovery Institute's Center for Science and Culture in Seattle. Let me remind that the Discovery Institute is probably the most prestigious institution in the field of intelligent design, or ID, all over the world. Now, it is impossible for me to summarize Professor Behe's outstanding career in the scientific field in just a few seconds, but let me just mention that he is the author of over 40 technical papers and of such fundamental books as Darwin's Black Box, The Biochemical Challenge to Evolution, The Edge of Evolution, The Search for the Limits of Darwinism, and most recently, Darwin Devolves, the new science about DNA that challenges evolution. Without further ado, let me just enter in the middle of things, asking Professor Behe to offer our viewers a quick recap on an argument that it is at the very core of the ID hypothesis, irreducible complexity. Why, Professor Behe, do you consider it a useful tool for detecting signs of ID in living systems?
Well, first, let me explain what I mean by the term irreducible complexity. An irreducibly complex system, although that's a fancy phrase, it stands for something simple. It just means a machine or a system or something that works and does things, but it's composed of a number of different parts. And all of the parts are needed for it to work. If the part is removed, then the system fails. And a good example of what I mean by that from our everyday life is just a mechanical mousetrap. If you go to a store to buy a mousetrap, you get the typical one has a wooden platform, and it's got a number of mechanical parts. It's got a spring and a bar that will strike the mouse, and when you push the bar over, you've got to hold it in place with another piece, which is called the holding bar, and the end of the holding bar has to be put into a little metal piece called the catch. And all of these parts are needed for it to work. If you take away the spring, if you take away the holding bar, if you take away the wooden platform, then it's not like you have a mousetrap that works, less well than it used to, or maybe just a fraction as well. It's broken. It doesn't work at all. So irreducibly complex just means you've got a lot of parts and they're all needed for a system to work. We see such things all the time in our life. Now, the problem, why this is relevant for Charles Darwin's theory of evolution, is that Darwin always insisted that his theory, his mechanism had to work in a gradual fashion. That is, he had an organism that was working and a little improvement came along, and that helped it survive, and it passed on this improvement to its offspring, and they had it and they passed it on, and this increased in the population until all of the offspring had it. And then another little improvement came along and spread throughout the population. So Charles Darwin insisted that changes had to be very gradual over long periods of time. And he did that because he knew that if one saw rapid changes in life and large leaps producing new features and new systems in living things, then it would look very much like something other than chance was involved. Something was directing it. So Darwin always insisted changes had to be gradual. But let's go back to the mousetrap now and say, how would you build something like a mousetrap in a way that was something like Charles Darwin's mechanism of small changes, improving it step by step? What would you start with a mousetrap? Would you start with just the little piece of wood that everything else is going to be attached to? But that doesn't catch mice. You might kind of imagine that, well, maybe you'll put a little piece of wood in the middle of the room, and maybe the mouse, when it runs over it, it'll trip and hit its head. But that's silly. It doesn't actually work that way. And then if you had this piece of wood, suppose you put a little holding bar on it. It's kind of a straight metal piece. And maybe you'd think that, well, maybe if the mouse tripped on it, it would, fall and impale itself, get stuck on the holding bar. But that won't work either. That's just imagination. So the problem is irreducibly complex systems can't be made gradually in a Darwinian fashion, step by tiny step, slowly improving their function. They've got to be put together all at once, or they don't work. And before everything's put together, natural selection does not have anything to select. Nothing's working. It's only when the system is together that it's helpful to the organism. But then natural selection and Darwin's mechanism doesn't have anything to do because it's already there. So irreducibly complex systems, if they existed, they would be big challenges to Darwin's theory. And it turns out, I talked about a mousetrap, but it turns out that pretty much any machine is the same way. If you think of other machines, maybe a food processor in the kitchen with little blades that turn around and a motor, or a computer or a car, or pretty much any complicated machine that you work with. They all have lots of parts that are needed. They can't be put together gradually, step by step. Well, the important thing is that science has discovered that life at the cellular and molecular level is run by machines. Literally, machines that are made out of molecules. There are machines that help cells swim through a liquid. There are machines that help take supplies from one part of a cell to another along highways that are built from molecules. So it turns out that the very foundation of life is run by irreducibly complex machinery. Darwin and his contemporaries knew nothing about that. They thought that life, the bottom of life, was just simple. When they looked at cells in microscopes in the 19th century, they saw little squishy, gelatinous substances. And they called the material of cells, they called it protoplasm. And they thought it was like jelly. It wasn't very complicated at all. So they thought something like that could change its shape and grow and maybe transform into something that their imaginations might think of. But now that science has discovered the molecular basis of life, we see that the cell isn't simple at all. and that none of the components of the cell can be built in the gradual fashion that Darwin envisioned. Just to give you an example of one cellular component that I like to speak about to audiences, bacteria swim by means of an outboard motor, just like a motorboat in our everyday world. And I mean that literally. It's not a figure of speech. In many bacteria, there is a motor in the membrane of the bacteria, the part that separates the bacteria from outside of it. And attached to the motor is a long hair-like structure called the excuse me, flagellum. And the motor spins it around and around and around so that it pushes against water, and the motion pushes the bacterium forward. And that propeller is attached to the motor by something called a universal joint, which allows the propeller to rotate while being connected to a motor that's at a different angle to the membrane. And the motor uses, for fuel, it uses a flow of acid molecules or acid particles from the outside of the cell into the interior, and that turns the motor just like water flowing over a dam can turn a turbine engine at the bottom. It turns it around and around. And the motor has to be clamped into position in the cell membrane so it doesn't turn while it's working, just like an outboard motor has to be clamped onto the surface of a boat as it's working. And there are clamps and other molecules that keep it in place. And there's something called a stator, which provides the rigid body around which the motor turns. So the point is that if any of the parts were missing, the bacterium wouldn't be able to swim. The flagellum would be broken, and that it, just like a mousetrap, it can't be built step by step in a gradual fashion. Another point to make is that many people have the impression that science has already shown how Darwin's mechanism could make life. But if you look in the science literature, in the journals where scientists publish their work, there aren't any papers that show how such a structure as the flagellum or many other molecular machines, how they could be built in the gradual Darwinian fashion that is the favorite theory. So it's really Darwin's theory is really just a social construct that everybody agrees that this is the theory we're going to use, but there is no good evidence that it can work the way it's supposed to. So it's a big problem for Darwin's theory. And one other point before I stop here is that irreducible complexity is also a good pointer to purposeful design, because when minds, thinking beings, have purposes, what they do is to take different components and they can place them in relationship to each other to produce something that will help fulfill their purpose. If you look in a dictionary, design is defined as the purposeful arrangement of parts. So when we see different parts arranged, like in a mousetrap, immediately we can tell somebody made that. Everybody who saw a mousetrap or an outboard motor immediately knows that they were designed. So irreducible complexity has two purposes. Number one, it's a big problem for Darwin's theory And number two, it's a strong pointer towards intelligent design.
Thank you, Professor Behe. This is a very, very fascinating argument in my view, and I think our viewers share the same feeling, hearing you, listening to you, explaining and describing these complex and simple, as you say, mechanisms. And I am fascinated by many things you said, but specifically in the first part of your answer, you said that at the time of Darwin and his first followers, like-minded people, they didn't have the same technical resource and findings that we now have to detect that kind of complexity. And so they imply that life is quite simple, that it will develop eventually due to some mechanism. Instead, you say that today, in the following years, decades, and centuries, and nowadays, we now have much more knowledge that can confirm that life is not that simple in its irreducible complexity. This is fascinating because many people say that critics of Darwinism and ID proponents are laid back, they look backward, they are kind of against progress in science. You're just saying the opposite. You're saying that we love progress in science and we want to progress because that progress will, bring us more light on things. Would you like to comment a little bit on that?
Sure. Yeah, that's right. Yeah, that's exactly right. Darwin's idea was good when he first proposed it. It was interesting. For all scientists in the 19th century knew it might have worked. But as science progressed, as we've learned more and more about life, we see that it's much more complex and much more sophisticated than Darwin ever knew. In some ways, it's like physics. In physics, Isaac Newton proposed his laws of motion and the theory of gravity and a lot of interesting ideas back in the 1500s, the 16th century. And they work very nicely at a certain level, at level of everyday objects. But then later on, when scientists acquired the ability to test Newton's theory at very fast speeds or very large objects, and tested gravity at long distances between planets and stars, they saw it didn't work very well anymore. And Albert Einstein instead proposed a theory of relativity, and other physicists proposed quantum mechanics because Newton's theory was not adequate to explain further results that science had discovered. In the same way, Darwin's theory works all right to explain small changes in life, in biology, but it did not anticipate the very sophisticated and complex machinery that has been discovered. It didn't anticipate that there would be DNA with information, literally information written into the DNA, which codes for the machinery of the cell. And as we learn more things, we have to reconsider our old theories. And intelligent design simply says that Darwin's theory was good in its day, but it's no longer adequate. And we can tell from the machinery of the cell that it was purposely designed.
Yes, thank you very much for these further comments. Let us remain within the realm of the very, very tiny. You mentioned flagellum and the cell. Let us remain a little bit in that realm. And considering that in your career you applied your scientific research to the parasite which is responsible for malaria, a very bad disease, and you applied your research to that parasite in order to understand better the way researchers and doctors fight against it. You then came to the conclusion, if I'm not wrong, that the malaria parasite is an outstanding example of the strong limits, again, of the evolutionary explanation of life as a whole. Can you brief us a little bit about that? Can you explain us why?
Sure. Yes. Well, if you're like myself, and you can think that Darwin's theory can explain some things, and it can explain, small changes in life, but how much, but other things in life clearly required intelligent design, like the flagellum and other molecular machinery that I discussed just recently. So how can you test what Darwin's theory can actually do? Instead of just imagining or theorizing what Darwin's mechanism could do, what's a good example, or what's a good experiment or test that we can see if how much it can do, or if there are good limits to Darwin's mechanism. And I wrote in a book called The Edge of Evolution that the best evidence we have for what Darwin's mechanism can do is from the genetic changes associated with the disease malaria, both in humans and in the malaria itself, the malarial parasite. It turns out that the malarial parasite is just a little single-celled organism. And as most people know, it's carried by mosquitoes, and the mosquitoes are infected and they get sick too. So they're not, we shouldn't blame them, but the malaria makes them sick. And then when they bite humans, the malaria is transferred to people, and it starts to grow in our livers, and eventually it goes into our blood. And a malarial cell goes into a red blood cell, and it starts to eat the hemoglobin that's inside a red blood cell, and it uses that to make copies of itself. It makes about 20 copies of itself, and then it breaks open the red blood cell. It bursts, and each of the 20 new malarial cells attaches to another red blood cell and goes through and makes copies of itself. And in the next round, 400 cells break out. And then the next round, 8,000, and it goes up exponentially. And in this way, it can eat a large amount of a person's blood. And that's what causes the problems. And as many people know, humans have had genetic mutations that were selected to help resist malaria. The most widely known as the sickle cell mutation. That's a small change in the hemoglobin of people. And there are also other changes like thalassemia, which is a change in the hemoglobin gene. And these genetic changes allow people with them to be more resistant to malaria than folks without them. So it turns out that Darwin's mechanism, things like that, can help in some circumstances. But it turns out those are pretty limited, because to make sickle cell to resist malaria, you just need one little change in a molecule called hemoglobin, which is already present in our bodies. But in my book, I focused more on the genetic changes in malaria that have come about because of the antibiotics that we humans developed to fight against malaria. And the most famous one is chloroquine, a drug called chloroquine. It turns out that chloroquine was first produced after World War II, and it was a miracle drug. It was wonderful. People were given some chloroquine, people who were close to dying from malaria, and they would recover quickly. And it was terrific. People, the medical doctors would distribute the drug, and malaria was no longer a problem. But eventually, after 10 years or so, the malaria started to become resistant to chloroquine, and it would no longer be killed when given the drug, the chloroquine drug. And eventually, all malaria was resistant to chloroquine, and the drug was worthless. The malaria would ignore it. Now, it took 10 years for that to develop, and if you read, it turns out that every year about 1 billion people become infected with malaria. And in each person who is sick with malaria, there can be 1 trillion malarial cells. So every year on Earth, there are an astronomical number of malaria cells. And nonetheless, it took all of these cells 10 years to develop resistance to malaria. But as I wrote in my book, there's another drug called atovaquone, where if you give atovaquone in a laboratory, if you put it in a test tube, it will kill all the malaria in the test tube. But if you give it to a person in a clinic who is sick with malaria, it might cure one person, but the next person you give it to, it doesn't. The malaria will stop growing, but then it comes back and reinfects the person. It develops immunity in just 2 people. It doesn't take 1 billion people worldwide, and it does it in a couple of days. It doesn't take 10 years. So it turns out that if you do the mathematics, malaria develops resistance to this other drug, atovaquone, about 100 million times faster than it did to chloroquine. It does it right away. But chloroquine, it's very, very difficult. So you ask yourself, why is it so difficult to develop resistance to this other drug, chloroquine, and easy for atovaquone? And the answer was just discovered in the year of around 2002 or so. And it turns out that in order to develop resistance to the drug atovaquone, you just need one change in one particular machine in the cell, a particular protein. But for chloroquine, you need 2 changes. One change doesn't work. If you have one change, the chloroquine is still, or the malaria is still susceptible to the chloroquine. You need a second particular change in order for that to happen. Now, it turns out that the human genome is very long, has a lot of information in it. It has about 3 billion DNA letters. So in the first instant, you need to change 1. And so the likelihood of that is 1 in a billion. But that's actually easy to do because there are so many malarial cells in a person. But to get 2 changes, like one needs to do for malaria, you need 1 in a billion times 1 in a billion. You not only get the first rare change, but you have to get a second rare change too. It's like winning the lottery, like a person winning a lottery and then having to win it twice in a row. You know, that's not going to happen very often. Suppose you had to win the lottery 10 times in a row in order for to win a prize. You had to match the numbers not just once, but 10 times in a row. You'd have a real difficult time doing it. So the point is that if one tiny change is needed in an organism, then Darwin's mechanism can take care of that. It's pretty good at just changing one thing. And we can understand that in human resistance to malaria, you just needed one change to get the sickle cell mutation, and that helps people resist malaria. You just need one change to get thalassemia, and thalassemia changes, they help resist malaria too. There's several other genes where you just need one change to get resistance to malaria, and they can happen and they can be explained very nicely by Darwin's theory. But if you need just two changes instead of one, then Darwin's theory becomes very less powerful, much less powerful. It has a very difficult time accounting for that. And if you need three or more, then Darwin's mechanism simply won't work. Now, the problem is, I explained in the first part of the interview how all the molecular machines in biology and the cell need a lot of different parts in order to work. So in order to develop those, you would need many, many changes. And so those are clearly beyond the ability of Darwin's mechanism to produce. So the point of thinking about that is to acknowledge that Darwin's mechanism can do some small things, and it can be medically important. It can help humans resist malaria. It's also responsible for genetic diseases like sickle cell disease, but that it cannot account for the sophisticated and complex machinery that science has discovered in life.
Thank you. Thank you very much. It's, again, very much illuminating. Well, so far we have spoken of the past, the research you've done, the conclusion to which you came in your book and your research. But what about the future? The future of your future in the ID research? In which direction are you presently going?
Well, right now I'm most interested in determining how Darwin's mechanism usually adapts organisms to changes in the environment. As I just said, Darwin's mechanism can do some things, but it can't make the sophisticated machinery of the cell. But how does it usually work? We know Darwinian biologists have told us that large changes have been seen to occur in animals in our history. For example, in dogs. It wasn't long ago that there were no dogs, and then wolves were domesticated, and the dog kind of was descended from the wolf, and many different breeds of dogs exist which are very much different than a wolf. We have little dogs like Chihuahuas, and we have large dogs like Dobermans, and we have dogs with curly hair like French poodles, and many different breeds. So how does Darwin's mechanism, or how does mutation and selection do that? Additionally, we have other changes. We know that, say, for example, polar bears are descended from brown bears or grizzly bears. And how does that happen? What exactly is going on? The interesting thing is that Darwin didn't know anything about genetics. He didn't know about DNA. He just had to guess about how changes occurred and were inherited by organisms. But now science not only knows about DNA, but only in the past 20 years, new laboratory equipment has been developed where the exact lettering of DNA, the billions of nucleotides, billions of DNA letters in an organism's genome, can actually be read and decoded by scientists in laboratories. And it can be done pretty easily, and they can be compared to each other. So that has been done only in the past 10 or 20 years. And interestingly, if scientists who are interested in evolution have sequenced the DNA of different dog breeds. They've sequenced the entire DNA of Chihuahuas and French poodles and bulldogs and other breeds, simply because they wanted to look to see what genes had been changed. And it turns out that most of the changes that are responsible for the dog breeds are where pre-existing genes that had been there in a wolf and other dog breeds, are broken and rendered non-functional. And that can cause changes in the organism that can be helpful. For example, if you wanted a small dog, you could breed dogs until you saw one that was smaller than usual and take that and breed that with other small dogs and maybe make something like a Chihuahua. Well, it turns out that small dogs are ones that have genes that usually make it full size. You can break that gene and then the dog will remain small. If you break a gene involved in making the dog's fur, sometimes instead of being straight, it will turn curly. If you break a gene involved in developing the muzzle of a dog, then its face will be flat, like a bulldog. So it turns out that the great majority of the changes seen in dog breeds are not due to making new things, they're due to breaking old genes. So instead of evolving, the dogs are devolving. Well, you might ask yourself, well, is that just because we humans are incompetent at breeding dogs? And turns out, no, that's not the case. That's the way nature works too. In my newest book, Darwin Devolves, which was published in 2019, I begin with the example of the polar bear. A polar bear, as I mentioned, is supposed to be descended from the grizzly bear or the brown bear. And scientists have now sequenced the entire genome of the brown bear and the entire genome of the polar bear, exactly because they wanted to see what genes had to be changed to make a polar bear from the brown bear. And of the top 17 genes that were most important in changing the brown bear into a polar bear, 3/4 of them were ones that were broken or degraded. The first gene, the most important gene, the most highly selected gene, was one that stopped pigment, brown pigment, from accumulating in the polar bear's fur, and that turned the fur white. That was very important. It helped adapt the polar bear to the snow and polar environment, but it was the breaking of a gene, not making a new one. The second most important change was in a gene that was responsible for absorbing cholesterol from the stomach and transporting it into the bloodstream. And that's important because polar bears eat a lot of fatty material, the blubber of seals, and there's a lot of cholesterol in that. And as we humans know, if you eat too much cholesterol, it can damage your circulatory system. Well, if the polar bears, the gene that takes the cholesterol from the stomach and puts it into the bloodstream is broken, and so they can eat a lot of blubber now. So it turns out that Darwin's mechanism, it seems, works chiefly by breaking old things, and kind of counterintuitively, that can help adjust an organism to its environment. Here's an example I like to use when people wonder how breaking something can help. Suppose you had a very nice car you were proud of, it was very pretty, but somebody came along and said that, you know, your life depends on your car getting better gas mileage. If your car doesn't get better gas mileage, you know, by tomorrow, you know, we're going to shoot you. And how could you quickly change your car so that it got better gas mileage? Well, you could take off the doors and throw them away, take off the hood and throw it away, decrease the weight of the car. Of course, the car would look a lot less attractive, and doors and hoods, they're useful in many circumstances. But if right now your life depended on your car getting better gas mileage, then throwing all those things away would be the way to succeed. And it turns out that evolution always works right now. It always works in the present time. It can't see the future. So the easiest way for it to adapt to many circumstances, most circumstances, is to break things, to throw things away, and usually that helps. So right now, my work is to go through the enormous amount of new work, new genetic sequencing that's being done because of improvements in machinery and instruments in the laboratory, and document all of these cases of devolution that occur, and that will get a better appreciation for how Darwin's mechanism actually works, and get a better feeling for the division between Darwin and design in life.
Thank you so much, Professor Behe, for this very charming anticipation of your work, and we look forward to follow you and read the conclusion and all the inferences of this new research, possibly in a forthcoming new book in due time, or some papers. And we do thank you for your time with us today. I remember our viewers that we just spoke of the intelligent design hypothesis with Professor Michael Behe, who is professor of biological science at Lehigh University in Pennsylvania and senior fellow at the Discovery Institute. We do thank him very much, and we give you we call for a meeting with our viewers to the next to our another episode of our series on this channel of CID, Centro Italiano per l'Intelligent Design. Thank you so much, Professor Behe.
Thanks very much for having me.